How's it going, everybody? Mr. D here, and in this video we're going to be talking more about first and second derivative tests to figure out where are we increasing and decreasing, and what are intervals of concave up versus concave down, intervals of concavity. Just as a reminder, concavity describes the bend of the curve, so concave down is kind of a frown shape, concave up is kind of a smile shape. To figure out concavity, you first figure out the second derivative. Where is that negative? We'll tell you where is it concave down. Where is it positive? We'll tell you where is it concave up. Anytime we switch concavity, so switching from concave down to concave up, the moment at which that happens is called an inflection point. Whenever you switch from concave down to concave up, or vice versa, you get what's called an inflection point. At that moment, your second derivative is going to be exactly equal to 0. The only other time your second derivative will equal 0 is if your function had a linear component. All right, so let's take a look. We're just going to figure out intervals of concavity here. Looking at the original function, I can already tell it's going to be a negative cubic, so this is my rough shape. So we're going to have concave up, inflection point, concave down. Let's figure out where is that inflection point going to take place. Start off some straight up power rule to get the first derivative. Negative 6x squared plus 12x. Second derivative then would be negative 12x plus 12. Now I want to figure out when is that second derivative equal to 0. So we'd set that equal to 0 and solve. I'm getting x equals 1. So I know at the x value of 1, that's when my second derivative changes from negative to positive or positive to negative. So I want to figure out what's going on before 1, what's going on after 1. So numbers less than 1, numbers greater than 1. And I'm going to plug those values into my second derivative function, which is negative 12x plus 12. Let's plug in 0. Negative 12 times 0 plus 12 is a positive value. So that means I'm concave up. Let's plug in 2. Negative 12 times 2 plus 12 is a negative value, so that means we're concave down. So we start concave up and then switch to concave down, which is spot on with what I thought my graph was going to look like just based on the type of function. So we are concave up from negative infinity all the way up to 1 because our second derivative is positive, greater than 0. We're concave down from 1 to positive infinity because our second derivative is, forgot of x, is negative, less than 0. The inflection point takes place when x is 1. But we need to figure out what is the y value of that inflection point. Well, to figure that out, let's just take our original function, and we're going to plug in 1 for x. So this would be negative 2 times 1 cubed, that's just 1. So negative 2 plus 6 times 1 squared, that's just 6. Negative 2 plus 6 minus 3. Let's see, negative 2 plus 6 is 4, minus 3, I get 1. So we have an inflection point at 1, 1. Let's take a look at another example that's been worked out for us. X cubed minus 3x plus 1. We take our first derivative, 3x squared minus 3. Our second derivative, 6x. Set that equal to 0. We get x equals 0. So that is an inflection point for our graph. Now this graph, just from the formula, I can tell it's a positive cubic function. So I already know it's going to have roughly this shape behind it. If I know the inflection point, I know that before or after that value is when we're going to have negative versus positive concavity. So to figure that out, I would plug in some value less than 0, negative 1, negative 2, something. Some number bigger than 0, 1, 2, 5, take your pick. And then we just need to evaluate, is that value negative or is it positive? That will tell you the concavity, and we can justify by claiming our second derivative is either positive or negative. Then to figure out your inflection point, you're going to take that x value from when your second derivative was equal to 0, and you're going to plug that back into the original function. And that's exactly what we did here. So we're plugging 0 into our f of x function, x cubed minus 3x plus 1. In doing so, we get an inflection point of 0, comma 1. All right, for this next one, we're going to start off just by doing the derivative. And then I've got the nicely written out stuff that we'll kind of scroll over to after the fact. All right, so first, let's get our first derivative, 3x squared minus 18x minus 21. Now this example wants me to also figure out increasing and decreasing intervals along with extremes. So I'm actually going to have to take a moment here to solve this and set it equal to 0. Before I do that, though, I do want to get the second derivative. So since I'm already on a derivation roll, let's just kind of go through and get that real quick. Getting 6x minus 18. All right. So for first derivative, let's figure out when is this thing equal to 0. I'm noticing there's a GCF of 3, so I can take that out. So then this would give me 3 times x minus 7 and then x plus 1, which means my x values are going to be x equals 7 and x equals negative 1. Now, I'm going to go through, and on my number line, I'd plug in negative 1 and I'd plug in 7. I'd figure out what's going on with any number back here. If I plugged in negative 2 for x, is this positive or negative? What's going on? I'd plug in a value in between negative 1 and 7. 0 is probably the easiest bet. Figure out, is this positive or negative? What's going on? Some number bigger than 7. Plug that in. See what's going on. If I backtrack a second here, the original function is a positive cubic. So I know it's going to look something like that. And what we just found are these values here. So that's going to be negative 1 comma something and then 7 comma something. So it looks like we're going to be increasing, then decreasing, then increasing. All right, now let's get our second derivative solved. I'll set this equal to 0. 6x minus 18 equals 0. Solve that, we'll get x equals 3. So then we'd go to our second derivative and we'd plug in a value less than 3. Probably 0 is probably the easiest. Is that positive, negative? What's the concavity? Plug in a number greater than 3. 5 would probably be easy here. Positive, negative, what do we get? Knowing what the graph looks like, we can already kind of predict, it's going to switch from concave down into a concave up. And what we found just now is that moment at which it changes, aka that inflection point, has a value of 3 comma something. Now to get these y values for these extremes, or this inflection point, I'm going to have to plug in negative 1 for x and see what I get. I'd plug in 3 for x and see what I get. I'd plug in 7 for x and see what I'd get. So that's going to show up here when I kind of put up the answers. If you don't want it to be spoiled, feel free to pause the video here so that way you can check your work with the answers that are going up there. So here we have the answers. At negative 1 and 7, our first derivative is equal to 0. At negative 1, we switch from positive to negative slope. That means we have a maximum at negative 1. We're switching from positive to negative, so we have a maximum at negative 1. To figure out that y value, you'd plug in negative 1 for x, and you get 0. At 7, our first derivative was 0, but we switched from a negative slope to a positive slope, so we switch from going downhill to uphill. That is a minimum where that happens. So that would be 7 comma negative 256. Wow, so if we plugged in 7 for x here, get negative 256. Both of those, again, knowing that the general shape is going to look something like this, both of those would be local extrema. So a local max and a local min. I'm going to plug that in here. So local or relative, if you prefer to call it relative. All right, second derivative. We solved for 3. Anything less than 3 would give you a negative concavity. Anything greater than 3 would give you a positive concavity. That inflection point, to figure out that specific y value, we already know the x value is 3. To figure out that specific y value, we would plug in negative 128 into this function right here. All right, we're going to go ahead and put the brakes on that, on this video here. I believe this example is going to show up in the next video, so hopefully you don't get too upset that I'm skipping that one. You know the drill, folks. If you have any questions, let me know. As always, good luck, have fun, be safe, roll tide.